All right, so let's get started. Last time we talked about exponential family and generalized linear model for fully observed Bayesian network. I think the take-home message from that class should be that, well, we basically decompose our learning problem to set up very modular small problem. And the first one was basically learning the parameterization of the single node, and the second one, learning the parameters of the conditional node. For a single node, we said that we really like exponential family that looks like the exponent of the distribution is as follows. Um, So we mentioned that many of the distribution that we have seen so far comes into this form. It has very nice properties. For example, the maximum likelihood estimation is basically computing the moment of the basically expectation of the t, which was our sufficient statistic, and this a, which is the log partition number, has very nice properties. For generalized linear model, we said that, well, that's the main connection between exponential family and regression. So let's say that we have x and y, and we are interested to estimate p, y, and x, given x. So we mentioned that this is basically a variance of the regression with a different link function. And we had this diagram that if we parameterize a function of the mean, so for example, a function of the mean of this distribution with a linear function of x, we can basically compute the maximum likelihood in a very closed form. And so we had this diagram that we had w, which is parameterization, x, that is what we are conditioning on, to eta, which is eta is nothing but w transpose x, that is connected to the mean of this distribution. And mean of this distribution is so related to the parameters. So this was a natural parameters, and this was a standard parameters, and they are connected through a. So this was a inverse. This is a prime. Sorry, this is a prime inverse, and so we had this diagram last time we discussed it. But I think that the take-home message at the end was that if you are given a graphical model, a directed graphical model that looks like this, at the end of the day, learning these parameters of fully observed graphical model decomposes into a set of factors, and you can solve them independently. That was the take-home message from the last time. Now we are making a contrast to what we have this session on learning undirected graphical model, and we see why things get a little bit more complicated. So this is the same diagram I showed you last time. We start with data, we model it that come from our insight, and we learn the parameters. And during the learning, we have to do inference. So for Bayesian network, we really didn't need to do inference, but for undirected graphical model, we see that learning and inference are intertwined, and we have to do that in a loop, basically. So we are going to talk about maximum likelihood estimation for undirected graphical model. We'll talk about our setting first, how our data look like. The entire talk today, we are going to assume that the model is given. So the structure of the model is given, the parameters are not, and we want to learn the parameters. So what are the examples of the data? So let's say that we want to do part of speech tagging, and we are given a set of sentences. And so, for example, time flies like an arrow. And we are given, so these are basically your data that are given to you. So you're given a sentence, and you're also given a tagging for that. So, for example, you ask somebody and say, hey, I think that the time is known and the fly is verb. You ask somebody else, he gave you different tagging, or gives you different tagging for different kind of sentences. So you are given the tagging for each sentence and also sentence itself. So you have set of this. It doesn't have to be the same length. Just this is how your data look like. So there is no hidden variable. Everything is observed. And also the model is given. So in this case, if you want to do part of speech tagging, you're assuming that the words next to each other are related to each other, words that are next to each other. This is a very simple model. So the word influences, so basically the tag of the word influences the word next to it, on the left side of it or right side of it. And you're assuming that the model is given. There is no ambiguity about the structure of the model. You just want to fill in the parameters here. So each of these have its own parameters, and you want to learn it. So again, we talked about, so a couple of sessions ago, we talked about the Gibbs distribution. We talked about like when you have under the graphical model, you can write the distribution as a multiplication of the clicks. But these clicks are not conditional necessarily, so you have to normalize it. We had this log partition number, right? Okay, so now the objective is we want to do maximum likelihood estimation given the data, which is data is here, and now the labels of the part of a speech tagging, for example. So all of the random variables are observed. You want to learn theta, and we are going to write it as a maximum likelihood estimation of the theta. The setup clear? Okay. So this is the objective that we are trying to optimize. We had the form of P, which was the Gibbs distribution, and we want to optimize theta. So most of the session today is going to be about optimizing that guy, theta, with the form of loss function, which was basically this. All right? So let's get started. So during the talk, I'm going to talk about different types of optimization based on the structure of the graph. Is it discrete or is it not? What are the general form? And different behaviors of this optimizer and when we should use what. All right, so during this talk, we are going to do inference. So let me recap the inference. So we had different kinds of inference. One of the examples of the inference was computing marginals, either marginal of one variable, which looks like this. So for given variables, you have to integrate out the rest of the variables. So that's a marginal, or marginalizing a click, which is a subset of the variables. Again, it is another form of marginal, except that xc is not just one variable, it's a set of variables. That was an example of the marginal we discussed in a few, I think maybe last week. Another important examples of the marginal is computing this partition function, the normalizer, that again, we can view it as a marginalization, as a inference, because you have to integrate out over all of the random variables, and if you do it naively, it's going to be very expensive, but we talked about click tree and the variable elimination. Hopefully you remember that. And there was another type of inference, which was, back then we call it maximum probability assignment or maximum and posteriori estimation, that basically instead of this summation, we want to find the best probability or like a highest probability over all of these configurations. This was, in a nutshell, these three kinds of inference that we have. We're going to use this inference as a sub-module during our learning, and you will see that. All right. So as I told you, I'm going to talk about, so our setting is that the data is given, there is no unobserved random variables. All of the variables are observed. And we want to learn the parameters. The structure of the graph is given, so you're not learning, you're not trying to find the optimal structure. Although if there was time, I'm going to talk a little bit about that at the end, but most likely we won't have time for that. And as I told you, there's no unobserved random variables. So the question that we are trying to answer in this talk is, well, the form of the objective is MLE. So it's a log probability, and the probability is a Gibbs distribution. And we are going to talk about what kind of optimizer we can deploy in this setting. Why is it difficult compared to fully observed Bayesian network? And a couple of tricks to make the optimization either faster or more tractable, and so on. All right, so the setting that we are, I can divide the entire talk today into two groups. One group I'm going to talk about discrete random variables, which you can view it as all of the random variables in this graph are taking discrete values. So, and I'm assuming that in this undirected graph, each of the clicks has its own parameters. So, for example, if I have a graph like this, so in this setting, I'm assuming that the state of each of these nodes are discrete, it's not continuous, and each of these clicks has its own parameters. So this is why you see two index here, that this is indexing things by the click, and this one says like this state. So, for example, if I have a click of 3 dimension, the parameterization of that would be what? If it is discrete. If it is one-dimensional, what is the parameterization? How does the parameterization look like if it is discrete? It's a vector, right? Right? So if it is this click would be what? Matrix, and if it is 3-dimensional, it's going to be tensor and so on and so forth. Right? Okay. So what I mean by theta c xc is that for a configuration that is specified in xc, go find out the corresponding click and read the parameters. That's all. Right? It's like go find the parameters in the table. That's what you want. Yes.
So for like a few vertices, you still can represent it with a matrix, right?
Yes.
Okay, so you don't need necessarily tensor.
Well, if the click is 3 nodes, then I need tensor. It depends on the size of the click. If it's only 2, I need a matrix. If it is 3, I need a tensor. If it's 4, I need tensor of 4 over 4.
Don't you write the values that they take and in front of that the probability that happens?
So this is not a probability, though. We are talking about undirected graphs, so this is not probability anymore. It's just quote-unquote affinity or happiness. So that in parentheses. But the way that you represent it, I mean, of course, you can, the same way that you do it in, I don't know, Python or MATLAB, you vectorize. There is no difference between viewing it as a vector. But the number of parameters is basically proportional to the size of the click, right? Okay. So I'm just giving you the notation, what I mean by this notation. So theta c means that parameter of the click c with the configuration xc. Clear? Okay. So this is the first setting. We are going to talk, in the first setting, we are going to talk about discrete random variable, discrete UGM. So first I'm going to talk about the easy case that things quickly can be solved without any inference and is a nice graph. And I'm going to make it a little bit complicated by talking about IPF. And I'm going to extend it for not even, so in a setting 2, things are not even discrete, can be continuous or can be discrete. And this is basically more general setting 2. Okay, so this is the recipe or agenda for today. So the first, okay, so this is exactly what I said. I talked too much before going to slides. All right, so let's start. So let me write down the structure of a graph called the log likelihood of the graph called model for you. I guess then from last time that I realized that you don't have enough time to go over everything. I'll write down part of it, so I'm going to use part of that. So this is my notation. I'm using curly D to represent all of the observed random variables. I'm going to use a little bit of like a little arrow on the top of it. So this super index represents one observation, so one sample. So let's say one tagging of the boards. So x1 through xn is different observation. Let's say different sentence that's given to you. I'm going to use arrows on the top to emphasize that this is a multi-dimensional randomized all of the random variables. So the dimensionality of x is more than 1. It's all of them. Okay. So during the talk, I may drop that arrows because it's hopefully obvious from the context. I'm assuming that each of these xi's, so Sorry for that. So this has to be I, are coming from IID from the property distribution or Gibbs distribution. Hopefully you remember the Gibbs distribution here. That's something that we discussed last time, is multiplication of all of the factors with the normalizer. And going back again, we want to find the optimal parameters theta in MLE setting, which is maximum likelihood estimation of the log of all of this data. And as I told you earlier, this data is IID, hence I can write the log of the joint distribution as a sum of the log. Right? So far the setting is clear? Okay. So when I write it as a Gibbs distribution, so I have two terms. First term is this term that when you take a log of this, it shows up as a sum of the clique. And we are, for a moment, I'm not assuming any discrete or continuous random variable. You can do it for any general undirected graph. I'm not even assuming that each of these variables are, each of these cliques has its own parameters. Just this, for now, we are not doing anything. We just like maximum likelihood estimation, take a log and just expand it. That's it. So we have a term that decomposes over the clique, but we have a normalizer that is shared. And that is the troublemaker. The problem here is that in the so if you remember in the Bayesian network, I think when I was showing here, if you are viewing each of these as a clique, each of the cliques are normalized probability, are they conditional or marginal? They are normalized. So there is no z or partition function that join them all together. So this is why when you have the data for each of these, you can solve for this problem, solve for this problem, solve for this problem, ignoring the rest. Here, the problem that we have, because of these terms, the log partition number, all of these terms are joint. So although each of these cliques may have its own parameters, you are combined through z. And so much of the talk today would be how we can handle this. But there are some interesting properties out of this. So let's expand this z. So remember that our z is our normalizer. So basically this z is that to compute this z, I have to sum over all of the state here. And this is basically my z. Right? So I'm going to write my z here. So summing over all of the states in my UGM of unnormalized clique multiplication. So this is the form of the distribution that I'm trying to learn. Okay? Now, what we are going to do here is we are going to make a gradient of L function. So let's start taking a gradient of this log n function. So I'm going to start this because I've cluttered this area a little bit. I'm going to start. You guys see that? Okay. Okay. So if I take a gradient of L with respect to clique C, so the only terms that stays there is you guys still see that? Okay. Okay, this is the gradient of the first term. Gradient of the second term. So I have to basically, this is z. I have to basically compute the gradient of the theta, the z theta, and the gradient of the second term would be simply gradient of the z respect to theta c dc, right? That's it. Yes.
I think there's a sum missing in the first one. Sum over cost first.
Well, no, this shouldn't be, right? I'm taking gradient with respect to the sixth parameter. So that's the only guy survived. The rest of them died. Right?
Oh, with respect to tendency. Okay.
Yeah. Okay. So what is the challenge is making a gradient of this guy, right? So now remember what z look like. This was how the z should look like, right? So if I take a gradient of that with respect to c, I'm going to get c prime not c, because that's the only term that survives. Is this part clear? It's a multiplication of the sum of the cliques. The only sum that has theta c stays. And I'm taking sum with respect to one variable, so we need, of course, this guy. Right. Right? Is it clear? Any questions? Yes.
What is that one? The last one that you just added?
Well, I'm taking gradient with respect to theta c, right? So if I take a gradient with respect to theta c, it's only one term. Is a gradient of that term, and the rest of them are not dependent, they're just multiplied. That's the only term that you can take a gradient. The other ones are not functions, right? Is the setup clear? Yes.
Where did the denominator come from?
Well, it's a log, right?
Okay, yeah.
Is a, okay, so maybe okay, sorry for that. Yeah, so I was taking the log of this guy, log of z. All right, so you see that, but okay, what is the right, so I can multiply this theta c and divide it and complete this term, right? Let's do that. So let's multiply it by theta c. If I multiply by, I can multiply it by yc theta c. Right? This term is this term. I just add it and multiplied it. Right? Multiplied it and divided it. That's all. Okay. What do I get here? Huh?
Z.
No. This term all together. This. So this is z, I agree. This is z. And this is the denominator, right? What is it in total? P, right? Right, so look how my P looks like. Yeah. This is how my P look like, right? Multiplication of all of the cliques divided by z. So again, I get the same thing. The denominator z and the denominator is basically all of the multiplication of all of the cliques except some correction term. Right? Okay. So all right. So what I get here is that I get multiplication of yc theta c divided divided by phi c theta c with p, this guy is p of y theta, right? And also, right. So I think something that I forgot here. There should be a sum here that I forgot. Okay. So now, what is this term?
Derivative of log of.
There's the the derivative of the log of pi yc yc, right? So, and this, so the derivative of this, right? The derivative of this. And in total, what is this? In total. So I have a term that looks like this. What is this term? It's like an integral, right? No, it's expectation, right? It's the expectation of what is inside of this. Right? Huh? Square information? Yeah, so it's like I can write the whole thing as an expectation of log of pi c yc theta c. Right? That's what it does. Huh?
So over there, when you marginalize like line above,
Yeah.
that ends up to be p of yc.
Well, this is how the p of yc looks like, right? The p of c is when I add the phi c, it completes the term. It has all of the cliques, right? If I have all of the cliques and divide it by sum over all of the cliques, what do I get? I get probability itself.
Yeah, I know, but
Huh.
if you scroll down to
Scroll down.
Yeah, to
Yes.
the bottom. Okay, so that one, the p of y and theta at the end, that becomes over the marginalization because it becomes p of yc and theta, right?
So this is summing over all states, not discrete, all of the states.
I know, but the function is only dependent on yc.
Yeah, sure, it's a function. Whatever function that is, right? It's just a function, but you're taking expectation with respect to everyone. Is expectation of that term inside of that function that you're taking integration or summation with respect to. It's just definition of the expectation. Right? Okay. So going back to what we had here, so let's substitute that in. Here, we take expectation. Again, you have seen this before. What is this? This is the log of phi c xcn theta c. And this was, the gradient of that was look like expectation, right? The second term. Okay. So this term, because we have a sum over it, is not function of the data. I can put the n here. But when I'm taking a summation of with respect to all of the data, this looks like empirical, right? So at the end, what I get is this. So right? N times empirical. N times empirical mean versus n times real mean. This is my gradient. So the nice things about this is that this is my gradient of my likelihood. And when I achieve the minimum, if I set it equal to 0, it means that my empirical should match my real. Right? So in effect, what I'm doing here is that I'm computing empirical, I'm computing the real. Also, whenever these guys match, I'm at the optimum. But the things that I'm optimizing, this sort of a score function is a log of potentials. Is the setup clear? Yes.
Why one of those phi is a function of x and the other one is y?
Well, this is the data, and this is a random variable. There's nothing random here. I mean, other than coming from empirical. But here it's just a number, right? When you're taking expectation, you're taking with expectation, which is with whatever which is not random, right? Clear? All right. So now let's talk about the discrete random variable. So let's talk about a special case which is discrete. Remember the categorical distribution. That our categorical distribution look like this. That a bunch of numbers like between non-negative numbers exponentiated to the indicator function, that if the value of that indicator function is k or not. That's probability of x being t. Right? That was how our categorical distribution looked like. And of course, we need to normalize it, but that's how it looked like. So now, let's think that our UGM is discrete. So there's no continuous, everybody is discrete. So all of the cliques look like something like this. So I can write each of my cliques as follows. So basically, each of my cliques look like multiplication over all possible configuration of the values of the clique. So if it was discrete, I have k values, it's going to be k. If my clique is more than one, so let's say if I have a clique of this, and this guy is k-dimensional, this guy is n-dimensional, how many multiplication I'm going to get here? Kn, right? So because it's going to go over all of the configuration. So if you have a gigantic clique, it's going to be exponentially big multiplication. But never mind, that's how we are writing it. So, and xc, we are assuming that these are observed values. These are our original setting. And this is the value of the cliques. So here, I'm not showing it as a general function because I'm talking about a specific setting. In the previous, in a few minutes ago, I was talking about the general setting. I was not assuming any continuous or discrete. But here, I'm focusing on a discrete. So phi c's are the values of this table that you have. You just put in your yc, and you read the corresponding values in that table or tensor or whatever that is. Okay. So if I write the log likelihood function, I'm going to have a sum over the observation, cliques, and all of the different possible configuration within each clique. So if you have a gigantic clique, this guy is going to be big, right? Number of cliques, number of observation, and how big each of the cliques are. So of course, if I take a log, this guy is going to come on the left, and this is the log of the value of that inside of that table, or tensor, or vector. Is the setup for discrete clear? Okay. Now, so this is how our log likelihood looks like. We have the loss function. Which is the loss of the values of the cliques minus log of the log partition number, and the log partition number was as before. There is no difference. So let's take a gradient of this.
These notes here are going to be uploaded, right?
Everything will be uploaded. So our loss function with respect to phi's, sum over n samples, cliques, all of the possible values of the within each cliques, an indicator function that says that if yc is equal to a specific configuration, it is observed in the data. And the log of the value of that table for the yc. Honest log. Okay. So if I take a gradient with respect to phi c of my loss function, n is going to stay. It's only one of the c's. So because I'm taking the derivative of just one number, it's going to be phi c yc. And for n, you have already seen that, but okay. Remember how the z looked like? It was summation over all of the terms, like here. And so now if I take a gradient of the z, so what do I going to get? So I'm going to get, so remember how my z look like? So I'm going to work out only this term. So it's going to get similar trick that we did last time. Summation over c not c, because we are taking gradient with respect to c, and phi c's yc prime, and sum over all of the y c prime c prime prime. Okay, so I want to complete this term, so I'm going to multiply it by phi c divided by phi c. So I'm going to get this term, which is my probability of p y theta, and so I don't get the gradient of that because I'm talking about one number. So because of this sum, okay, so I'm going to get y minus c 1 over phi c. Okay. See. Okay, so I get the same thing again. It looks like expectation. So you have a probability, you have some function, and you're integrating all of over all values. Sorry, it shouldn't be c prime. So again, it looks like expectation of 1 over phi c. Okay, so the same thing is basically you're getting the same thing, except here. So what do I get here? So let me focus only on this term for a second. What is these terms? This is count, right? The number of times that I've seen configuration yc. Except it's not normalized, but I can normalize it. So I can multiply, so it's like I over 1 through n. I can multiply divided by n, and I'm going to get something. I'm going to introduce a notation here. I'm going to introduce a notation. I call it empirical. This is the notation I'm going to use for empirical of YC, which is number of times that I've seen this specific configuration, which is 1 over n. 1 YC is equal to this specific configuration.
Why 1 over n?
I'm going to introduce that. It's just normalize it. This is like what you have seen here is exactly the same thing multiplied by n. Okay. And what you see on the other side is, so this is this term. The other term end up being, so the first term become n xcn, and the second term become n probability of yc divided by yc that we used for correction. Okay. At the optimum, if I set the gradient of yc equal to 0, these should become equality, and also get rid of that. So I get the same thing of empirical being equal to, okay, I'm missing something, okay. So I get something slightly more specific. So what I got here is that, I think there is something missing here. So I got something more specific. I got empirical, so if I'm given distribution, if I go over all of the samples and count the empirical distribution of an observation, and I do, given the parameters, I do inference, at the optimal, these values should be equal. So, and you can also see that in what we had here. We had empirical, we had the expectation of this score function empirically being equal to actual value. So if the empirical distribution is exactly the same as the actual distribution, these logs become the same because the values that you're taking expectation of is the same thing. So if empirical become the same as your actual probability distribution, they match. And this is what you see in a very simple setting for discrete random variables.
Where did the log go?
Huh?
Where did the log go? There was a logarithm there.
So the logarithm here, so there is here, the values of, there is no logarithm because it's not a function, right? It's just a value. The logarithm of the value is like 1 over that value. There is no logarithm. We had the logarithm in the previous setting because we didn't want to have any explicit parametric assumption about phi. Here we're making explicit assumption, it's just a number, right? What's the log of a number? What's the derivative of the log of a number? It's 1 over that number, right? There is no log. Okay, so this will give us basically a condition. It's a condition that at the optimum, that the gradient is equal to 0, our empirical should match the marginal. So, so just saying the same thing here, that if I take a gradient of the phi c, I get the empirical divided by phi c, I get the probability divided by phi c. If I set it to 0, this is the condition. The empirical distribution should map the marginals. The problem here is that it just gives you a condition. At the optimal, you should have this condition. It doesn't tell you how to do this optimization. It just tells you at the optimal how the behavior should be. Now, how we can make an algorithm out of it. So first, I'm talking about the easy graph. In the easy graph, and then I'm going to extend it. So hopefully, from the previous talks, you remember this quick tree. So let's say that we are given a UGM with these 6 random variables, and I want to write it as the Gibbs distribution of that. So the Gibbs distribution of that would be multiplication of all of the factors. So there's going to be 1 factor another factor, and so on and so forth. So hopefully you also remember the notion of the click tree. So I can write the click tree of these as follows. I have one click here, and one click here is the maximal click, one click here. So each of the, I'm going to make a click tree out of this. The first click is a click of first random variable, and the second one. The second one is the click in the center is a random variable, is a cluster of x2 and x3 and x4 and so on and so forth. So we had the cluster of the random variables. We have separator, which we also call it subset. And this was our junction tree. So there was something interesting about this kind of graph. So if you remember, we had this specification in the lecture 6 that if we can write a graph as a junction tree, the probability distribution of that is decomposable. So for example, we have two clicks here, this click and this click. So the simple click tree for this distribution would be ABC and BCD, and the separator would be BC. Now, what is nice about it is that I can write the probability distribution of the join of PABC as the marginal of each of these clicks divided by the variables that are separating them. And there was a generalization of that if I have a junction tree, a decomposable graph, the definition of that would be I can write the joint probability distribution of all of them as multiplication of all of these the clusters divided by the separators. So going back to the example that we had before, so I can write this as multiplication of the joint distribution. Remember, this is the distribution. You're talking about the distribution, not factors anymore. I can write it down as a multiplication of this guy, this guy, this guy, this guy, divided by the separator, which is this, this, and this. But here we're talking about distribution. What is interesting here is this. I can start absorbing these terms in the denominator into the denominator and decompose this graph. So let's do this. So I can start merging these two together. So what would I get if I merge these two together? Yes, so I get P of x1 given x2. Okay, if I merge, let's say, these two together, what do I get? 2 and 5. And the same with this, right? Okay. I can do this, and I can write my UGM as sort of like a PGM with some weird thing, except that it's not everything is conditional. Well, it's multiplication of a bunch of conditional and marginals. These two become this guy, which is the probability right now. Is not an unnormalized factor. It's a probability. This is the term which left, which is marginal of the 2, 3, and 5. And the other term, so on and so forth. So what is nice about this is that if I want to fit the parameter, so now going back to the distribution that I have, this is the term which involves x1 and x2. This is the term that has x2, 3, 5, like this. This is the term that has x2, 4, 5, like this, and so on. What is nice about it is that if I take a log of this, it decomposes. So for this case, I don't need to do any inference. It decomposes, and I can learn the parameters empirically. I can match the size. Remember the condition that at the optimal, my empirical should match my marginals? I can just match them without any inference. So, and this is basically called maximum likelihood estimation by guessing. If your graph is nice, which means that's decomposable, like the example that I showed you, you can start merging these terms together. Just fit the marginal with the probabilities, you're done one shot. The conditions are that, as I told you, the graph should be decomposable. Not all the graphs are decomposable. I'll give you an example. And the clicks should be defined on the maximal clicks. Remember that we had the design choice of not defining the clicks on the maximal clicks because saving the parameters and whatnot. But if it is defined like that, and if each of the parameters of the clicks are different from each other, you are not sharing any parameters among them. If all of them satisfies, you can magically, with using the same trick that I told you, fit the empirical to parameters and done with the learning. Yeah.
So you're assuming you didn't tell how to do that matching. You're going to say that, or?
No, I showed you how to do matching, right? I showed you at the previous slide that at the optimal, your marginals should match the empirical. This is decomposable, and the parameters are not shared. This guy has a different parameter than this guy. I can go and find the empirical of each of them, match them, and have the parameters. Because that's the problem. This is the condition at the optimal. Right. So what are the examples of non-decomposable graph? Here is a very obvious example. This graph is not decomposable. You cannot interpret the potentials as the marginals. Do people see why it's not decomposable? Why is not decomposable? Well, is not chordal, right? If there was something from here to here, I was fine, although there's a loop. And also clicks are defined over the join. So if I have a chord and my clicks was defined like this and this, I would have been fine. But because it is not, the graph is not decomposable, I cannot do the same thing. So what should I do? So now I'm going to talk about IPF, which is basically a fixed point algorithm. So what is fixed point algorithm? So let me explain the idea of a fixed point algorithm in a general setting. It's very useful for solving general problems. Of course, it's not always converge, but we'll show that it will converge in this case. But the recipe is like this. You want to find the optimal of, let's say, cost function j. You take a derivative of that. And you have to set the derivative to 0, right? You write the terms and make sure that, so you want to basically set the gradient to 0 and find the optimal theta. You expand f and find one of the single f. You set it to the other side of the variable, and that's your fixed point. So let me give you an example. So let's say that this is a function that I want to optimize. It's a polynomial of order 3. If I take a gradient of that, it's going to get a quadratic. I mean, of course, you know how to solve the quadratic, but let's play with this. So now at the optimal, this should be equal to 0. So here we go. I singled out one x. You want to find the optimal x. I'm going to move x to the other side and get this equation. At the optimal, this should be equality, right? So what I'm going to do is that I'm going to compute the right-hand side, set it to x, and repeat. It's very easy to implement, right? Because you just find the x, find the right-hand side, put it to the left-hand side, do it again. And it's just basically a couple of lines of code. And yes?
Isn't this just Newton method?
For optimization, it's not the Newton method, right? So the Newton method has a Hessian and all. It's a fixed point algorithm. It says that this is the condition I want to satisfy at the optimal point. My theta should be equal to this, to some hairy function on the right-hand side. So if I just do it again, so this is exactly how this is one of the approaches that you can solve, I'll get back to you, for eigenvectors, right? So you say A V equal to lambda V. So I can say that 1 over lambda AV equal to V. Again, so I have A, I don't have V. I have some estimate of lambda. Just hit it with the matrix until they fix. Yes?
There may not be a closed form solution, right?
Well, this is for the case that there is no closed form solution. Right? If the only hope for you to have a closed form solution is that the graph is decomposable. We are talking about the cases that the graph are not decomposable. It's a numerical approach, but it's very easy to implement numerical approach. I have to say, it does not, so you cannot say that, oh, well, that it seems that we have a recipe for our optimization problem, let's apply it. It does not always converge, but there is a proof that I'm not going to show you that for our case it's going to converge. So let's go back to our case. Remember that we had this loss function, and we take a gradient with respect to the parameter of the click C, and we get this condition. Remember that? Okay. So, in fact, we get our condition was this. That was our condition, right? I can multiply and divide by phi c to get something look like a fixed point iteration. At the optimal, I'm just basically writing the same thing here, just multiplying both sides. Now, if I want to do fixed point trick, I can say that compute the right-hand side, put it in the left-hand side, and do it until you converge. Although it may sound like a hack, but it is not. In fact, you can show that in every iteration, you are reducing the decay loss function. And I'm not going to go to the proof, but if you're interested, it's in the book. So this is basically summarized IPF. So, all right, so the only catch here is that to compute this, you have to do inference, right? The denominator is empirical. You just see the data, you count it, and you put it in the denominator. For the denominator, you have to compute the marginal of the click. And you have to run with the current parameters that you have to run your inference algorithm. So it's basically the general algorithm is like this. Run the inference to get the marginal of each of the clicks, run the fixed point until you converge. That's the general algorithm of the IPF. So again, going to properties of the IPF, we are assuming that each of the clicks has its own parameters. We are solving it with the fixed point iteration, and you can prove that it's a coordinate ascent. You can prove that in every iteration, the loss function, which is your MLE loss function, increases with very simple operate. And it's not a hack, so it converges. But the thing is that in every iteration you have to compute this denominator, which means that every iteration with the current parameter you have to compute the marginals. Yes.
So coordinate descent, you wrote in brackets. I'm not sure. You mean just like you get a block of coordinates and you do that over it?
Yes. So remember that we are optimizing the parameters of the click. So it's a bunch of parameters. So we are not doing one parameter at a time. We just identify a click, say, update all of them at the same time. This is why it's called block. Yeah. All right. So now, well, all of this works for discrete case. What about the continuous case? So for the continuous case, we are resorting to a specific type of representation, which are actually quite general. And this is for the case that the clicks can be represented as an inner product of the parameters with some feature function. So here I'm representing the parameters with some feature function that you designed it prior. We'll see an example of that in this class and also in the following classes. So this is the setting that I'm going to talk from this point on. So far, as I told you, I've only talked about the tabular case or the discrete case, that the clicks potential are just like a vector or a matrix or a tensor, and you're just optimizing these parameters with IPF algorithm, which is a fixed point iteration. Can I extend the IPF for continuous case? So also another thing is that, like, you may ask, well, I only deal with the discrete parameters. Do I need to care about continuous case? Do I need to care about this case that you can write the potential as inner product of parameters with the features? So the answer to that is that even in your world, everything is discrete. You still have to care about this because of the example that I told you, that if your clicks end up to be very big, you're going to have a gigantic parameters. Like, because even for two dimension become a vector. A click of 3 variables become a tensor and becomes big so quickly. So So if you cannot handle these many parameters, either you have to cut some edges in your graph and makes your graph artificially simple to get rid of the gigantic cliques. Or you can do something else. You can say that I can keep the parameters the same, but make the cliques smaller. Another solution of that would be using less parameters. So for example, in a graph that I showed you, you remember this? What if we share the parameters? So for every pair, it doesn't have to be, this is clique 1, this is clique 2. Who said that the parameter of the clique 1 and clique 2 should be different? They can share the parameters. This way you can reduce the number of parameters. So these are the case that this setting that we are talking about is very important and can be helpful. So this is called feature-based model. So give you an example. Let's say that you have a UGM, and I've given you, let's say, that the task of extracting, so let's say that I've written brace. Okay, so this is, let's say that I've given you each of these rectangles, and you have some feature extractor, and you say that, okay, this look like B, this look like R, this is C. Okay, so these are all clear. But let's say that if there is some ambiguity in the writing, you want to make sure that you don't only look at the features that you see on the image. So you want to do OCR, hand recognition detection. You want to say, you know that I've written in English, and you want to make sure that the things that I've written is already in dictionary. So for each of these characters, you have a possibility of 26 letters. So now, but you know, if you and you want to say that, okay, so if I want to design an OCR algorithm, I want to have all kinds of dependencies, because it's just like this is how I like it. So if you want to do it that way and you want to do it naively, your cliques that are all fully connected, even for 3 letters, going to have 26 to the power of 3 parameters, which are quite, I would say, fake, because there are so many configurations that are not in English. So it's just not feasible in a dictionary. So how can I take advantage of this knowledge into my graph? So for example, I know that if there is, I can say that this is a possibility, like a wildcard ED is like past tense of the word. So if I see patterns like this, is feasible. But if I see a pattern of like JKW, there is no word of that in English. How can I incorporate this in my graph? So the remedy to that is we can design a function or a feature that says that everything that is possible that you have seen in English, general pattern, doesn't have to be every single configuration. You can say that all of the words that are wildcard ED are somehow the end of the sentence. This is feasibility. You may not have any word with, I don't know, maybe TED you have it. Like maybe you may not have any word with WED. Actually, we do have WED. But any other words, I don't know. So come up with something that you don't know. So there are cases that are not possible. I can set all of those to 0, so that this is impossible, that this potential is impossible. And other possibilities, even is vaguely defined into feasible sets. So the advantage of that is that, first of all, you can, if you are creative, you can use this capability to rank different configuration. You can rule out some of the other possibilities. For example, in this case that I told you, that like you can set the feature of the JKX to all zeros. Like it's impossible. Right? You won't see that in English. And also another cool things about this is that you are reducing the number of parameters. So instead of accounting for all kinds of possibilities of the 3 letters end of the word in English, which is 2 to the power of 6, you define k, which reduces the parameters to k. How big that k would be. So for example, you can define a potential which says that all of the words that ends with ing, all of the words that ends with ed, and so on and so forth, and sum them up. That's one way of doing it. It doesn't have to be like that. But that's actually a very nice recipe to design features. So what is nice about it is that if you design features like that, each of these potential, instead of having multiplication of this, which is like 26, 26, 26, is going to have k possibilities, and a number of parameters is going to be k. There's a big reduction in the parameters. And you can sort of think of it as like a micro potential inside of the each of the discrete that says there are some configuration that I use a blanket. I say that these are impossible, set it to 0. So it gives you a lot of degrees of freedom to design. And also the nice thing about this is that you don't leave. So hopefully by now you notice that we are talking about the clicks that look like this. So your F is free based on your knowledge, but if your clicks look like this and you have a normalizer, okay, so let me write it. What does this remind you of? So what would happen if I take a log of this and bring it inside? I can write the same thing as exponential family,
Yeah.
right? So I can write it as theta c transpose fc xc, and then I can bring a inside, and I get something like theta c minus a theta, which is a is e to the power of a theta is basically z. Z theta is e to the power of a theta. So it's exponential family. So I can design my features and the joint distribution exponential family. And we know so much about exponential family. And we have a lot of nice tools on that. So these basically help us to say, basically, I'm going to design my sufficient statistic based on my problem. And the joint distribution sufficient is exponential family, and I know how to handle exponential family. So as I told you at the end, my joint distribution looks like this, which again looks like the exponential family. Let's say the measure of 1, hx equal to 1. And we can do a lot of cool things with this. But can I use IPF for that? So remember, we had IPF works for general discrete graph. But can I use the same thing? So we had this fixed point iteration for IPF. The answer is that maybe not exactly, but we can make modification to that. So I'm going to talk about the generalized iterative scaling, which is, you can see the generalization of the IPF. So the general idea, and I'm not going to go over the detail, is that instead of, so remember in MLE we have maximum likelihood estimation, and we want to maximize this maximum likelihood estimation with respect to parameters. So the idea of the GIS is that I'm going to lower bound it, and because I found a lower representation of the function that's always lower or equal to my maximum likelihood loss, but I know how to optimize it. So, and you, instead of going for maximum likelihood estimation, you can go for the lower bound. So basically, this is the objective function that you want to optimize. You want also, this is like a loss function of the MLE, but you find something else that is a parameter of data. So and is like is always lower than equal the loss to your likelihood, and you can say that I know how to optimize this easily somehow. If I maximize this, I'm going to basically maximizing the other guy too, because always lower bound. Okay, sorry. I said lower bound, I put up. Okay, so that's the general idea. And this, we are going to use this idea again and again for expectation maximization, for other ideas that you see in later on. So I won't go through the detail, but as I told you, we find lower bound, and the same idea of the fixed point iteration. Take a gradient, you identify part of the parameters that is singled out, just put it in the left-hand side, evaluate the rest, and substitute that in. And you basically get something which somehow looks like IPF, except at the log scale. So if I take a gradient of my lower bound, which is here represented at the bottom, I get the function look like that. And if I design my function so that the sum of my functions are somehow look like probabilities, like it's a specific kind of loss function that it's a specific type of features that normalizes. This is not arbitrary, I somehow normalize my features. Then my update is going to look like this. And why I'm saying this is like GIS, remember is like IPF. Remember in IPF, we had this condition at the optimum, which is multiplied by the current estimation and give us an update. We have something similar there, except that if you take a log of this guy, so the GIS look like the loss, look like the IPF in a log space. Next update, current update, log of the empirical by the marginal. The same here. Next update, current update, log of the empirical divided by marginal. So, well, you may say that, well, we know the whole thing looks like exponential family. Why not taking gradients? Just like put it in your choice of optimizer, your optimizer of choice, like, I don't know, like whatever that takes a gradient, like a TensorFlow or PyTorch, and take gradient, do a stochastic gradient descent. So the answer to that is totally possible. In fact, in most of the cases, it works pretty well. So the general idea here is that you have your loss function, you take a gradient, you have a gradient of your loss function, and use your, for example, stochastic gradient descent and optimize it, and use any other black box optimizer, Adam or whatever. And retrieve the parameters. Or if you have a luxury of you're able to compute the second order, then good for you. You can even make your optimizer much faster. So an example of that is you can use, I mean, I'm pretty sure nowadays all of you guys know enough about deep learning, and you know that one of the optimizer that works most of the time pretty well in deep learning setting is a stochastic gradient descent. You can do the same thing. So the general idea of stochastic gradient descent is that, well, you have the loss function that sums over all of the data. But if you wanted to compute a gradient and do this summation over all of the data, it's too expensive in each iteration. So in every iteration, you choose a subset of this subject to compute a gradient, and you follow, instead of going over all of the data. And most of the time, it works pretty well. In fact, in reality, it also works pretty well in this setting too. So to give you an idea of how the gradient in these settings look like, I think I've already shown you, but let me work it out again. So how does the gradient look like? So we have, so let's say for only one data, this is how our probability, log probability look like. Okay, so if I take a gradient of that with respect to click C, I get fxc, and what is the, so I get this t. As I told you earlier, z is e to the power of a. So the gradient of this with respect to z is going to be gradient of a with respect to theta c e to the power of a theta c. So what is this from last time? You have a log partition number, you have a partition function, you take a gradient of that. What do you get? Expectation. So the expectation of your xc. And this is still z, right? This is still z. And this z cancels out. This guy and this guy cancel out. So you get the same thing. For one random variable, with one observation, you're going to get the same form that you keep seeing during this talk today. So if I want to compute the likelihood over all of the data, so what I'm going to get is that I'm going to get empirical minus FC marginals, right? So hopefully you see that this term is easy, right? We just like have your function, just evaluate it, sum them up, you're good. This is hard because you have to compute the marginals and compute this empirically. So to compute this term, you need to run inference. But you have already told how to do inference. So if you have your inference module ready, you can compute this gradient. And whenever you have your gradient, plug it into your optimizer. You can use a stochastic gradient descent. You can use Adam, grad, whatever you want, and optimize it. Another thing which is quite important is that when you are writing as a loss function, most of the time you still have a lot of, so because although we are using feature function to reduce the number of parameters, but we still have a lot of parameters most of the time. So it's a good idea to add some sort of like a regularizer to your loss function. So it's not going to be exactly maximum likelihood, it's a regularized maximum likelihood. So you can say that instead of optimizing this, you can optimize some sort of like regularization of the theta. And there are multiple choices for regularization, such as L2, L1, that we are not going to discuss today. It's basically the same thing, but the difficult part is taking gradient of the likelihood. This is easy. So the practical point is being that in practice, if you have a lot of parameters, be careful on using proper regularizer that match your method. Although stochastic gradient descent, as we'll see a little bit later on in a class, that it has some effects of regularization as well. So in reality, doing a stochastic gradient descent do just fine. So here's an example that using the GIS algorithm, you have to go over more than 1,000 runs over the entire data. It takes 270 hours. Stochastic gradient descent just fine. So you may say that, like, why did you teach us GIS? So the answer is that if you have, again, I'm going to go back to what I said before, that if you have a features that sums to 1, this is going to work better. GIS works better. If you have a general features, don't do it. Just do a stochastic gradient descent. You are fine. So for a specific class of algorithm, GIS works pretty well because you are searching within a space of some funny properties. All right, so I think I managed to finish it. So we talk about two settings, setting 1 and setting 2. That the setting 1, we focus only on discrete random variables, tabular case. I showed you a nice class of the graph which were decomposable, that you don't need to do any inference. compute empirical, match them, and you're done. Also, I talked about the class of the graph which are not decomposable, but you can use this fixed point idea and solve it. We talked about GIS algorithm and basically reducing the number of the parameters with idea in a feature space. That, by the way, it's not just for continuous case. It works for discrete case and the continuous case. It's a great tool to reduce the number of parameters and make the optimization faster. And I told you that if you have a general graph and your features are arbitrary, just use stochastic gradient descent, and things gonna work fine. All right. So I have last announcement. There are other stuff at the end of this that I'm not sure I can have time to go through that without rushing to it. A couple of announcements. We have the deadline for the project. If any of you guys don't have projects, there's something that I think people ask several times. Max 3, I'm fine with people having only single person in a group or 2 person. That's fine, no problem. If somebody doesn't have a project and is interested in approximate inference algorithm, which I can talk about a specific project. But if you guys are all decided about your project, then you're good to go. Other than that, you're fine. That's the space. Thank you.